Get hopefully a prompt asking you if you're okay with the recording. So you go ahead and click that or leave, either way. But okay, so I hope the audio is clear. Can I have some thumbs up if the audio is clear before we start? That's great, thank you. And now I will be sharing my screen, which I hope you are seeing as well. Okay, awesome. Perfect. Okay, so welcome everyone. Thank you for taking part to this workshop, which I decided to organize about a month ago. I thought it would be a good idea to. I didn't know what I was thinking at the time, but I did organize it, and I think it's good because it's nice to have an overall kind of look at a whole sort of experimental approach from the start to an end of what it looks like, in my opinion, to design a well sort of designed experiment, and hopefully kind of going through the steps of what I also think are sort of bad decisions that sometimes are made when designing a good experiment, but also focusing on the good aspects. By the way, I'm looking off to this side because that's where my screen is and my webcam is this way. So I'm sorry if it looks a little bit off, but that's the best positioning I could figure out. This is how it's going to work. So it's a fairly long workshop, but I don't think that we will use the whole 2 hours. And if we do, well, there's that. But there will be time for questions. Shun, who I can see here, thank you for helping. She will be collecting some of the questions during the workshop. I will not be looking at the chat because that's too many things to look at. But what will happen is that I will stop at certain points and I will ask you if you have any questions, and you can ask questions there. But you can also type questions in the chat, and if they are of some sort of like time-sensitive nature, sort of like, can you repeat this because it's unclear, then Shun will let me know, and I will do that. But if they are sort of more, like if they can be answered later, then they will be answered later, so that the flow doesn't get broken. So this is 2 hours, and then I will remain afterwards to kind of answer more. I want to say personal questions, but I mean like personal project related questions. And this is more for people that are not from the department. So this workshop is open for everybody, really. So, if you are from the department, it's much easier if you set up a meeting. You're welcome to say and ask questions, of course. But this is kind of an extra, an extra step for people that don't have this chance, maybe on a daily basis, or just want to like run their experiment quickly by somebody else. And this has to be like quick questions. I don't have time to, of course, like run through your data set and things like that. But hopefully I can help somehow. Okay. This is pretty much it, I think, in terms of housekeeping. So I suppose that we can make a start. There's going to be the majority of this is going to be focused on the slides that you're going to see here. And then we're going to jump into our studio for a little bit, but you don't have to. The code is already written and just going to walk you through it. And even for those of you who don't use R, I'm going to try and make it more about the general point than the code. So if you don't use R, don't worry about it. It's, I'll try to sort of make a bigger story out of what I'm doing, so that even if, you use other analysis tools, or, this is still going to be something that it's going to, it's going to make sense for you as well. But if you do want to code along, for example, or if you want to download these slides and the code and the data that's attached to this, you can see that there is the repository at the bottom of this slide. So the ANSI / 2022 underscore DAW, which DAW made sense at the time, and I'm not sure what it stands for, design data analysis workshop something. But if you go there, so you have to go on github.com/ and then you put the name and the repository, then you will have the option to download, and it contains the slides, the source code for the slides, the data in the R code that we will see later. So you have, you can also, even for people that are watching the recording, they can do that as well. So it will remain available. So let's make a start. Unless there are some pressing questions or something doesn't work as expected on somebody's end, then you can speak now. Awesome. Oh yeah, and if you have questions, again, when I ask you, if you do have questions, you can just go ahead and speak. You don't need to write it in the chat, and I will try to get some of your participation as well at some point. And please just speak out. There's no need to like raise your hand. So if I ask you, can somebody tell me something, then you just go ahead and speak. So just a brief introduction. I see a lot of people are internal here, but there's also a few names that I haven't seen, and so it's good that again, and there's a recording remaining. So my name is Max. I work as a lab manager and a self-appointed data scientist at the University of Konstanz in the linguistics department. I mainly work on data and R. But of course, I do have some tasks as well in the lab, such as helping with recording, managing more sort of trivial aspects of the labs. But on a daily basis, what I do is I tend to help out with R, data wrangling and visualization and analysis. And I've been doing this for about a year and a half, plus or minus. And I've had my fair share of projects that I've seen and help out and sort of collaborated on. So I thought it would be a good idea to sort of maybe pool all of this experience together, which may not seem like a lot because a year and a half is a short period of time. But of course, I do have a PhD in linguistics where I've done mostly experimental and quantitative work, just as well as 2 master degrees in which I also done only basically quantitative and experimental work. So hopefully more of this experience pooled together. So here is a brief summary of things that I'm interested in, such as R, but also things that are more sort of meta research, such as reproducibility, open access, and in general good scientific communications. I think in papers, reporting your results, understanding the limitations of your study, I think is something that I'm particularly interested in. Also, just a few words about the Ling Labs. The Ling Labs is a consortium of laboratories here at the University of Konstanz. So it's not just one lab, it's a series of labs. Most of them working sort of both independently and collaborating on a variety of topics. So we have different labs, of course. Most of you are part of those labs, so you know about them, but we have the phonetics lab and the baby speech lab and the psycholinguistics lab and the neurolinguistics lab. And so many different type of research is happening throughout those labs. And it makes it a very exciting environment to work within, but also it kind of makes it better because you are exposed to so many different types of methodologies, so many different types of data analysis that it's nice to be able to take something from one type of experiment and kind of like try to innovate and move it onto different types. And now lately we are also trying to innovate and add more methodologies. We just purchased this really fancy mobile eye trackers, and we plan to do pupillometry as well. So there's a lot of exciting things happening here. And we're also organizing a series of workshops that are, again, sort of like this one. This is sort of an unofficial workshop of this methods series that I am sort of overseeing. But we have one workshop in June on data digital signal processing in R. That's taught by Chris Carignan from UCL, and you can already sign up for this. There will be the link down here, I think, but you can find it through Twitter as well. So you can already sign up for this for free. We have another one in September. As you can see, that one you can't sign up already, but it will also be free, and there's more planned. So keep an eye on that page at the bottom if you're interested, and you will find more opportunities for workshops. And these are open to everybody. Usually, internal people from the department have some sort of priority, but usually there's many spaces available that everybody can join. So. Right, so I have this analogy throughout this entire workshop between running an experiment and shooting a film. And To be honest, it's interesting because I'm fond of both things. So I'm a big, experiment person, but also I love, watching films and reading a lot of stuff about how films are made. Um, I think that as an analogy, you might think, okay, well, there are a lot of analogies between the two things, but why would they be useful? Well, I think that if you're new to maybe, running experiments, it's good to have some sort of like analogy to something that is better known outside of what you're trying to learn. And I suppose that if you already know about the different steps of experimental design, this analogy is not going to really help you that much, but at the same time it's probably not going to be detrimental. I had more fun making the slides, so just bear with me. So we will draw this analogy, and let's start. So now we're getting into the actual workshop, right? So this was just a whole lot of a long introduction, but now this is where the workshop is starting. So if you want to make a movie, there are different steps, and you cannot just walk from one step into the next and hope it will go well. A lot of these things have to be prepared, and they will have to be prepared from the very beginning. At the very beginning of a film, you will probably write a script or take a script from somebody. There are repositories where people go and hunt for the next movie hit, right? And find a script, and then when you decide to make that film, you need to come up with a budget. You need to figure out how much money you can pull together to actually make this film. After you have an allocated amount of money, you will most likely want to decide how much you want to spend for casting, and how much you want to spend for the location and the props you're going to use in the film, and everything. You'll need to draw up storyboards, which are kind of like it is sort of like you draw pictures of the shots you're going to take in the film to make sure that everything is planned in advance. And then once you have all of that, you clearly go ahead and shoot your film, and that might take longer or more or less time, and it's definitely a team effort. And so, but this is not the end, of course. After you shot your film, there is something that is as long, and as full of effort as the first part. And so you have to edit your film, and you have to color grade it, right? Which is when you sort of make it more homogeneous and kind of make it a whole one thing. And then you have visual effects, and you have so many things. And finally, once you're finished, you just bring it to a festival and hope it wins some prizes, and then you bring it to the press, and they will review it, okay? And I mean, if you know something about running an experiment, I think you already see many comparisons. And when we're creating these slides, I was actually surprised at the amount of comparisons and direct comparisons I could find. Again, it's really useful, maybe not, but I think it's an interesting thing. And I don't know if you have been watching this TV series lately. It's hands you put your hands in Zoom if you have. It's a great TV series. But I just wanted to show you something like this. Looks like a normal scene. It looks very effortless, but the amount of preparation, the amount of thought that goes into this, it's great. This looks like just a bunch of people hanging out, but when you start looking at the photo, you can see how, for example, the two people wearing a shirt are basically symmetrical to one another. The series is called Severance, and throughout the entirety of the series, there are so many aspects of severance, of people being split, and you can see how these divisions create a sort of perfect symmetrical scene, how the floor and the ceiling have as much space in this sort of shot as one another. And so everything in a movie which looks effortless, looks unplanned, is actually very likely planned to the smallest detail, including the color of the carpet, the type of lights chosen to light this scene, which look like normal light but probably aren't. So here is an example, and I would like to now sort of draw a comparison, a direct comparison between this that we've just talked about now and experimental design. So I would like you to sort of jump in the conversation, and perhaps just kind of tell me what you would think the counterpart to, for example, running an experiment for this would be. So what would you think the counterpart to sort of writing a script would be in the sort of experimental design aspect? Anybody, just please, unmute yourself. I think you are able to do that, right? I don't think I've locked the unmute button.
Would it be like a pre-registration?
Well, I think we start from maybe even below before that. Like this is just when you're starting to think about making an experiment. Um, so just think even earlier than that.
How would it be?
In the literature?
Exactly, right. So I would think like writing a script is more like your sort of research question, like literature part. Like that's the first step. That's the entire story of your experiment, and that's kind of where you always need to start. I think when writing an experiment, I think that this is pretty straightforward. I mean, we do have budgets that we need to think about when running an experiment, and I'm not necessarily talking here about just the money, but if you want to run an ERP experiment, well, you need to have access to ERP. If you want to run an experiment, a longitudinal study over 2 years, well, you need to be able to have access to these participants for the next 2 years. So this, again, fairly straightforward. So, again, you might not have, you have casting, you have participant recruitments, you have locations, especially now more than ever, you need to choose whether your experiment will be run online or offline, for example. And you kind of need to think about how all of that is going to work, come up with a design, a methodology, and then you need to collect the data, which is also just an important part. Finally, you have this data, you need to pre-process the data, you need to analyze the data, you need to visualize the data, you need to edit your data so that it comes out of an experiment, it never comes out ready to be written about in a paper. And then finally, as you can, this is pretty straightforward as well. You bring your paper to the press, or you bring it to conferences, really, instead of festival, I would assume. So we have this right here. So really, like, the most important thing that you should take away is a lot of issues in experimental design can be avoided if you plan ahead. Okay. Nobody shoots a film and then realize they ran out of money halfway through. I mean, I suppose it might happen, and there is very little you can do. And the same is if you are planning to do an experiment on something and then you realize that you have the wrong data, or you have not enough participants, or you have your research question is too complex, or you don't have the hardware or the software to analyze your data. And then that's where the majority of issues come. That's where it becomes very tricky to it's where you'll have to compromise to actually get to the finish line. So you want to make sure that you plan ahead every step of the way, and that everything is allocated, and it doesn't mean that you don't have to give yourself multiple options. So it doesn't mean that you have to know exactly what type of regression analysis you will use for your data. It's okay to say, well, I might be using different types of analysis, as long as you are aware from the start what your options are going to be at any given point, and you can give yourself sort of leeway in saying like, well, I know that if I get this kind of thing, I will do this, but otherwise I will do something else. Then it's still, I think, okay. But a lot of the times it happens that something you didn't expect happens, and something doesn't work, and then it kind of goes down from there. So if there is one thing that you can take away from the workshop, and really the one thing you should know, is to plan ahead. And that's pretty much all that I have to say about it. So this is the end of the workshop. Thank you. But of course, we are not going to do that. We are going to take it a little bit at a time. So we're going to go through each one of these steps that we talked about. And we're going to, it's difficult to have it's difficult to have something extremely specific to say about any of these aspects, because there are so many different types of quantitative research. There are so many different types of experimental research that I cannot just say, this is what you have to do, this is what's the best, because each sort of branch, each methodology, even within each branch, has what I call later sort of baggage, right? So there are certain things that you need to do, there are certain things that you need to do in a certain way when you choose a specific methodology. So hopefully you will get some general advice here, and then it is kind of your job to sort of be able to take this general advice and shape it accordingly to the type of experiment that you want to do. So there is no like 100% a correct answer for everything, right? So I'm going to give you some advice, a general advice based on my experience, of course, based on some literature, but it might be that for the specific case that you need, perhaps something else is better. So, always kind of apply your own knowledge and know your method, know the kind of experiment that you want to run, and you know best. It's impossible for me to know about every possible type of experiment that needs to be run in linguistics, right? There's so many different types. Any pressing questions so far? Okay, so let's start. And again, now what I will try to do is I will sort of move from the first, from the very beginning to the very end of this production, and I will have more or less to say depending on the topic. Again, things like the script, your research questions. I think those are so highly dependent on your field. They're so they're shaped by the field and the method that you're using, that there is no sort of one size fits all kind of advice that I can give. But based on my sort of experience seeing a lot of, especially maybe like students work or PhD students work, is that important that you have a very direct operation, way to implement your research question in an experiment. You can have the most exciting research question on the planet, but if you don't have a way to directly test it, it's going to be a problem. And you may think that this is a silly advice. Well, not silly in the sense that it's wrong, but you might think like, well, I mean, this is, really basics of running. Of course, I'm going to find an experiment that tests my theory. But if I put this other way around, how many times have you written a paper and the claims coming out of the experiment are way too generalized for the method, right? And so sometimes you think that your method is enough to for example provide a sort of generalizable discussion, a generalizable result, but perhaps your method is limited in some way, and for that reason your your generalization, your answer needs to be limited as well. If you are running an experiment on 2 participants, you can't generalize it to the entire population, whatever that population is. And so again, if you run a behavioral experiment, you might not be able to talk about the cognitive side of a specific phenomenon, because you maybe should have run an ERP experiment instead, or an fMRI or whatever. And it doesn't mean that it's a bad choice, but if you know that you have this sort of limitation in types of what kind of operationalization you have, then you should still scale down your research question as well. So the idea is that if your research question is too complex, scale it down or zoom in, perhaps focus on one aspect of a broader research question. When I started my PhD, my research question was merely to find out which aspects of speech perception were top down or bottom up. And it's a massive question that people have been trying to answer for, short of 40 years. And of course, it was an impossible task. And of course, what I ended up doing in my PhD was a mere fraction of that. But it's good to have of course, a sort of starting point, its general starting point, but then especially for the the implementation of that, one needs to kind of zoom in and scale down and sort of think in more specific terms. And so again, make sure that also you come up with hypotheses that are testable, because if you can't test an hypothesis, that's a problem with the scientific method, of course. And so now you have your research question and they can be implemented and they're great. And now you need to figure out how to implement this research question. So we have again here, for example, some of the way that I would consider this budgeting or this implementation is what kind of methodology would you decide to use to answer the research question, or how many experiments would you run? And so we have other example here, what experimental design and what variables, how variables are going to be coded. And I'm going to mention, talk a little bit about all of these things. So the method of an experiment is what, in my sort of analogy, I draw to the genre of the movie. And I think it's a great analogy because the method doesn't just determine how you will collect the data. A lot of the times, a method also comes with a lot of a baggage that basically determines how you will handle a lot of other things. Certain method requires certain types of data processing, specific types of data analysis. For example, ERP papers have a certain format when they're much shorter, for example, and things like this. So the method of your experiment doesn't just determine how you will collect the data. It's only a small part. It determines a whole lot of things. As I said, data processing, data manipulation, but also how to set up hardware and software. And so it's important that when you choose a method, you are fully aware of all of these things. So what the literature will help you to make sure that you know that when you collect ERP data, you need to pre-process it and filter it and downsample it and create epochs and then put the analog triggers in and sort of time align it and all this stuff, right? And if you don't know that, then you risk having problems. However, if you're on sort of the other end of this, so if you're not just starting out with your chosen method, if you have been using it for quite a while, don't be afraid to innovate either. So there are a lot of, I think it's good. The best advice I give all the time when people ask, should I do this? Should I remove outliers, or should I transform this data, or should I do this? Is check out the literature in your field and do what somebody who has a peer-reviewed publication on this has done, because at least you can, in a way, more easily justify your arbitrary decision. I decided to remove outliers because it's common practice and done by this and that. But of course, this is not a way to innovate. And if you are, if you're sure that what you're doing is good, and if you're, if you can justify it, if you can show how your take improves on the existing literature, don't be afraid to do it, because that's how we will, advance the field. So you want to decide as well what kind of experiments you want to run and how many experiments you want to run. I think that everybody tries to get as much data as possible in one experiment because nobody wants to run more. It's tedious, and you need to collect, you need to get participants in multiple times. But at the same time, it might allow you to get a simpler design. And a lot of the times, a way too complex design is what it was one of the major culprits of poor data analysis sort of capabilities. Because if you have an overly complex design, you might not have enough data to compensate for this, and so everything that you get out of this is going to be somewhat unreliable. But we'll talk more about this later. And in this case, I'm not talking about sort of, well, of course, if you have 3 different experiments to begin with, that's fine. But this is not what I'm talking about. This is more like, is your experiment like too complex that you might want to think splitting it up? So of course there are cases in which you already start thinking about having 3 experiments, and that's absolutely fine. But consider also sometimes might be worth splitting them up. And so once you have your you have decided for your method and you've decided what experiment, now it's the time to decide sort of the resolution of your study. And I think that this is probably one of the most important aspects. And again, if you have to take one thing home, take this one. And this is like, less is more. I know that a lot of the times when you're running an experiment, you're excited and you want to get a lot of stuff and you want to say, okay, I want to test, again, I don't know, let's say I want to test polar versus whatever rhetorical, it's the wrong example. I know nothing about questions, but I want to study, for example, loud speech versus whispered speech in acoustic terms. Okay, this is what I've done for one of my master theses. Okay, maybe we can also include things like the gender of the speakers. Okay, that's a fairly something common to add, right? Oh, but maybe we should also focus on how that changes on social aspects. And so let's get half participants are like middle class and half of the participants are working class. And maybe we should also focus on like young versus old. And maybe we should, and so you start adding so many predictors and you start splitting up your sample size in so many different ways, which eventually makes it very unreliable, because unless you can compensate for this, right? So the idea is that every time you add a predictor with 2 levels, and this is sort of the minimal example, you need to double your sample size. So if you're not taking into account, for example, you have 10 participants, let's say you have 10 female participants and you record this participant speaking loud and whispered speech, and you want to analyze the acoustic properties. And then you say, okay, actually, I'm also interested in young versus old. And so all of a sudden, you have, if you have 5 young and 5 old, you now have 2 groups, but these 2 groups have half the participants that they had at the beginning when you only had 10 female participants. And so ideally, what you would want to do is you would want to keep, if 10 is the correct sample size, then you want to keep that sample size going forward. So you now would want to recruit 10 young and 10 old. And now if you do have, for example, working and middle class, then you would want to have 10 young working class, 10 old working class, 10 young middle class, 10 old middle, whatever the last one was. And so, but most of the times you can't do it. And so most of the times what happens is that you start splitting and splitting and splitting. And now if you only have 2 predictors, that is already 2.5, on average 2.5 people per group, and you started with 10. If you add an extra one, you're already close to 1 person per group. And so what that means is that now you have 1 person per group, which is, I guess, better than 0. But at the same time, if that person behaves differently because people are complex humans, we cannot control for a lot of the behaviors, not all of the behaviors of human participants can be tied down to are they young and old or middle class or working class. Humans are, and that's why we, if you know something about modeling, that's why we have these humans or participant as random effect, because there are so many characteristics about humans that we cannot control that we want to tell the model this person is going to behave somewhat differently for something that we cannot account for. But then if you do have only 1 person in each group, for example, then you're basically left to the fact that if this person behaves differently, not because they're young and middle class, but because they're a human, then this is going to skew the entire group averages, right? So the idea is that the more participants you have, the more data points you have. Sometimes participants is not really what you're interested in. Sometimes it's okay to have fewer participants because you're doing, for example, like within subject design, and like an example I think is ERP, and most ERP experiments are usually run towards like 20 participants, and in many other fields 20 participants is a laughable number. But then with ERP, what you tend to have is 400, 500 trials per participants, right? And so at this point, if you're kind of more confident that participants are going to behave similarly to one another, you might sort of give up and say, okay, I'm going to give up a few participants, but maybe I'm going to increase the amount of stimuli that I'm going to have. And again, there is no kind of one size fits all answer, because this really depends on the study. Like I said, if you run an ERP experiment, 20 participants is not considered a low amount of participants. But if you run I don't know, if you run some other sort of study, then you might want to have hundreds or thousands. When you look at those, for example, medicine studies on, like, okay, does the effect of a vegetarian diet does it affect some illness down the line? And of course, again, like, humans are so complex that to account for just one thing, the effect of a vegetarian diet, you need to get so many participants, because each one is going to be different. Like, oh yeah, I have a non-vegetarian diet, but I also don't do sports, and somebody else has a vegetarian diet and doesn't do sport, and of course there are so many possible combinations of this that you need thousands, or if not hundreds of thousands, to see the effect of one thing given this, for example, vegetarian diet. And so one way to help you, and this is more of a practical tip, I suppose, one way to help you determine something like sample size is to look at power analysis. I'm not a big fan of power analysis. I don't tend to run them often. But this tool, so the CMAR package in R, allows you to if you run something like a pilot study and you have some idea of what your effect size for a certain thing is going to be, you can basically ask, if I want 80% power and I have this effect size, how many participants do I need for my study? Can I, and you can also do power simulation. So you can increase the amount of participants and then ask, okay, what if I have 40 participants instead of 20? Does it change the effect size that I get? What if I have 40 items instead of 20, but the same number of participants? Do I get a better, so you can sort of play around with that, and that can be a helpful tool to sort of help you maybe determine your desired sample size, for example. And for the Bayesians that don't like power analysis, but to be honest, I don't necessarily like power analysis either. Um, you know, one of the things that I always hear from, when talking about Bayesians is, if you run your frequentist model, statistical model, you always run into convergence issues, and if you don't, if you run Bayesians, you never have convergence issues, as if if you run Bayesian statistics, all of a sudden it doesn't matter if you have very little data. That's, it's kind of like a magic wand, and it turns out your results. And of course that's not what it is. And I think a lot of people that actually do Bayesian seriously know that. Of course, I mean, I would say everybody. But the idea is that, of course, even if your model always converges, even if you have very little power, your model converges. That uncertainty of not having enough data is going to show up somewhere else. So, in Bayesian, you look at credible intervals. And of course, if you have very little data, your credible interval will be much bigger. You will have a lot less certainty that your result is correct. Your model might converge, and it might not converge in the frequentist framework, which is basically telling you the same thing. There is not much going on here in just two different ways. So it's important that regardless of the approach, whether you want to do a power analysis, whether you want to look at your credible intervals, whether you want to just run a model or whatever, it's important to understand the limitations of having, for example, a small sample size. And a lot of the questions I get are, what can I do if I don't have a lot of participants? And the only real answer to that is you have to scale down your research question. You have to, if you wanted to look at whatever 3 or 4 different predictors, well, now you need to scale down. You need to make your model whatever simpler. You need to limit your ability to to generalize. And I know this kind of hurts because you've done your experiment and you want to, and the problem is you also have a lot of pressure from journals. So if you don't have an exciting result, if your result is a null result, then nobody wants to publish your paper. And so there is unfortunately a huge push to sensationalize your results, which I think is doing the scientific community a huge lack of favor. And we've seen that with the replicability crisis in psychology, where 80% of papers cannot be replicated. And we see it every day across linguistics too. It's because if you there are so many things that could go wrong in an experimental design and a data analysis that if we're not honest with the results that we have, we just tend to have this misalignment between the reality and what we have. And so again, a few other tips here. Again, know your limits, and this applies to both the methods chosen and the experimental design. So if you don't have access to a specific methodology, if you're new to a specific methodology and you don't have support, know your limits. But it doesn't mean you shouldn't do it. It should just mean like be extra careful. I did a PhD on event-related potentials, and I didn't have any direct support with event-related potential in my department. And so, I knew that, and I knew there was a limitation, and it created a massive sort of how do you say, issues with imposter syndrome, because I was, going to so many workshops and learning about this, but I never had a huge, direct training in that. And so, you have to be extra careful if you don't have a lot of support, and seek resources in learning how to use your method correctly. Also know your goals, because that will help you shape your methodology. I think, it happens quite a lot. that people want to be extra in their design. Especially I see it for when maybe you have like this sentence comprehension test and you're looking at a specific thing, let's say and then you're saying, okay, but like, what if we try and have both questions and affirmative, whatever? And what if we have both negative and non-negative? And what if we have this and that and this and that? And you end up creating this, 2 by 2 by 2 by 6 design. And, and ideally, now you would want to get something like 200 participants, but you don't. And so the issue there is, it's okay to just say we focus on, questions this time, and we don't look at any other sort of aspects, or we focus on just negative, whatever, or whatever. And so I think it's because eventually you think you're doing yourself a favor, but you're not, because eventually you have such a complex design at the end, and what you can get out of it is sometimes unreliable on all fronts, because instead of focusing on one thing, now you have 10, but on each one of those 10s you cannot reliably reliably comment, because your amount of data is limited. And we mentioned this before, registration is something it's more and more say up and coming in linguistics. So you can have a registered report. So a registered report consists of a lot of more journals now are accepting this. So you write your paper before you collect your data, and you have your method section, you have your literature section, your hypothesis, and you can submit this to a journal, and you can get it pre-approved. So your paper is somewhat already accepted before, well, it's not somewhat, it's already accepted before you collect your data, as long as your methodology and hypothesis and research questions are clear. This is very helpful nowadays for what we were saying before. So a lot of papers don't make it to a journal because you have null results, but null results is very useful. Null results are very useful in advancing science. I can't imagine how many people have run the same study independently so many times because they looked up whether something happened, they didn't find anything, and it turned out that maybe there was a non-significant result, and so nobody ever got to publish it.
Max?
Yes.
There's a question in the chat.
Yes.
I was just wondering, Max, sorry to interrupt, why you are so skeptical of power analysis, especially pre and post experiment.
I think power analysis, the main issue with power analysis is the effect size requirement, right? And so, like, I've run it myself, but the idea is that with the power analysis, so you have 3 elements in the power analysis, right? You have the power, the effect size, and the sample size. And usually you need to know 2 of them to determine the 3rd one. And so if you want to know the correct sample size for your study, you need to know, well, the power, which is easy because it's 80%. That's usually the threshold that we consider to be an effective minimum power level for a study. But then you also need to know the effect size that you are going to get in your study. And let me tell you, that's not something that's easy to do, especially if you don't have a lot of literature preceding your study. But even then, the same effect might be found at different strengths or degrees of strengths, depending on the type of you're not going to run. I think it makes sense, if you run like the exact study somebody has run, and then you can say, well, they found this exact, this much of an effect size. But if you already change the methodology a little bit, you might expect a slightly different result than somebody else. And so even if you use the literature, which is your best bet to determine somewhat of a reference effect size, then you're still not, you're still guessing somehow, right? I think that's
couldn't you kind of guess like accurately to say like worst case, mean case, best case, effect size? Like that's what I try to do, like literature kind of. And post experiment, like why is it not handy also to say like, guys, there was not a lot of chance to actually find anything because it was really the power actually establishing it post experiment? Why is that so?
So you mean like when you use the effect size that you found, for example? Well, this is something that was done for a little bit, but there are actually a few articles. I don't have the references at hand, but I can try and find them later, on how post-hoc analysis basically, what it's really telling you, it's the same thing as the p-value, because you're basically asking what is the possibility, what is the power of finding an effect size that I found with the sample size that I have? And that's basically like asking, what's my p-value? You know, the p-value is already kind of like the, you know, I mean, it's not that, but it's, you know, in very, very simple terms, the probability of finding, you know, as an extreme of an effect and stuff like this. So I don't think it's not useful, but I don't think it's more useful than the kind of information we already have through the p-value. And so the idea is this, and you can try this in SIMR actually. So if you have a significant effect, you are going to likely already, if you run a post-hoc analysis, and so you say, I have an effect size of 0.4, 20 participants, and that effect is significant, you're always going to have enough power. The result is it's going to tell you that you already have enough power, because all that it's kind of telling you, it's the same as the p-value. So it's kind of telling you, yes, you have enough power to find a significant effect, which you know you have found already, if that makes sense, right?
So yeah, I just showed it, like I saw it other way around. If you didn't find an effect in articles, they then report, well, we didn't find effect, but you know what, we didn't have enough power. So it's kind of used as an excuse sometimes to some degree.
I know exactly, but that's yeah, absolutely. But the problem is that's also like one of the options, right? I think when you don't find an effect, you definitely could not have enough power, but you also could just not have the effect, and those two things are very, yeah. But no, but it's a good point, and I've used it as well in the past year a few times. I just think like use it a little bit skeptically, and don't kind of, I think like, especially in psychology, people rely on it way too much. You know, I've seen a lot of, you know, every time I see somebody who submits a paper into some psychological journal and then they get it back, and there's always like, where power analysis, you know, like, give me my power analysis. And I'm not a big, you know, I wouldn't use it as a sort of like, you know, necessary, you know, it can be useful, but it's not the answer to everything, I think. Is that okay? Any other questions before we move on, since we're already answering some questions? You can just feel free to jump in, and here is a few references for the registered report things. Okay. So we, yes, so here is another important point in my opinion, and something that I do see as an issue quite often, is variables being coded in a way that it doesn't necessarily work well with the experiment. And I think that it's something that is fairly, you know, simple and achievable compared to what we were talking about before, as in like, you know, if you don't have the material to do ERP experiments, well, you can't do them. But, you know, in this kind of thing, you know, everybody can sort of like take a little bit extra time and think on how they want to code their variables. And for example, here I have a few examples, right? So you have a binary variable instead of a continuous variable, or some Laguerre scale of some sort. You have a Laguerre scale instead of a binary variable, and you know, there are many possible combinations. And I don't think that any type of variable is worse. I just think that sometimes you want to make extra sure that the type of resolution you're looking for is, you know, is the one that you actually need. So I've done some experiments as a participant where I was asked to, you know, for example, say whether something is grammatical or non-grammatical, and it's 100-point scale. And it's like, well, for me, it was either, you know, 0 or 100 every time. And if it wasn't 0 or 100, it was a misclick. You know, it ended up being just a misclick. And so why, you know? At the same time, you want to make, I don't know why my video turned off. I'm not sure. At the same time, you also want to make sure of the opposite. So if you do have the opposite of that, then, for example, you might not want to have yeah, so you get the point. Try to make sure that you code your variables the way that you are wanting to use them later. Can you guys still hear me? Because I'm having issues with my video for some reason. Okay, that's back. Okay, it works now. I'm not sure why it stopped. Okay, right, great. Sorry. Okay, so in a way, in a way, there is a side to err on here. So in a way, it's always better to have more resolution than less. So ideally, if you do use a 100-point scale and what you really wanted was a 5-point scale, you can still somehow do that later, right? You can say from 0 to 20 becomes 1 and 20 to 40 becomes 2 and so on and so forth. If you do the opposite, then you have an issue, because then you have a 5-point scale and you can't divide it further back into 100, right? And so the same idea, you know, if you have a continuous variable, you can later bin it. That's when you take, for example, and you say from 0 to 100, let's make it, you know, yes or no, for example, or true or false or whatever. But you can't do the opposite, right? So if you have a binary variable, you can't go back and bin it. But I wouldn't necessarily, well, you know, then the solution to me, I wouldn't just go and say, all right, well, then I'll just have everything be a 100-point scale, and then I will sort of simplify later on, because I still do think that what type of variable, what type of scale you use has an effect on the participant during the experiment. And I guess I should have found some reference. I don't actually have references for this, but I would imagine that a forced choice between two options and a scale between 1 and 100 sets different expectations somewhat, and also leaves, you know, has different types of effects in the study, right? You can force somebody to say yes or no, rather than giving a, you know, an I don't know kind of answer, sort of sitting in the middle, which I would recommend 90% of the times. Please use, I think most of the times it's always good to have just like forced choice, you know, especially in the sort of behavioral stuff that we do in linguistics. I find that it's, you know, instead of having like an I don't know answer, because especially now you're left with maybe a categorical variable with 3 levels. So sort of like yes, no, I don't know. And now it becomes a little bit more clunky to analyze, because if you have 3 levels, then you need to use an M-logit, so a multi-something logistic regression, which is not great to do in R. If you do frequentist, if you do Bayesian, apparently it's very easy. So you know, you can go ahead and do that. But and also, like, what do you really do with this I don't know things? You know, it really depends on the design of the experiment. But I would go as far as to say, well, then design an experiment that doesn't require this I don't know answers. Design this experiment that forces a choice. But anyway, again, this really comes down to the specific type of experiment, so we can talk about it, you know, personally when we talk about your experiment, if you have questions about this. Okay, let me just go back here. Right, and then there's 100, you know, other examples, and so again, like this example, for example, if you know you're using frequentist statistics, and you put you have a variable with 3 levels or 4 or 5, it's going to become a little bit tougher to analyze, which is fine as long as you are aware of that in advance. I get a lot of people coming to me and say, well, you know, my dependent variable is 4 levels. What do I do? And now all of a sudden your sort of workflow becomes a lot more difficult, because like I was saying, this M-logit analysis is not part of the more common packages in R. It requires a whole different packages, but those packages are somewhat limited, so you're not able to have things like random effects and so on and so forth. So it's worth keeping that in mind. Okay, I guess I'll just use this camera. Okay. So let's move on. Okay, and now we arrived at the production level, and the production level would be your, you know, your data collection. Do we have any questions now at the end of this section here? We're sort of halfway through now, I suppose. No questions. Okay. So, like everything, I think you need to find a balance, and you know, in a way, it is kind of like compromising. But ideally, you would always compromise before you run an experiment compared to after. No experimental design is going to be perfect the way you want it, because there are so many limitations. You can only have so many stimuli before your participant starts hating you. You can only have so many participants until you run out of them. You know, you can have only so many type of combinations, and sometimes you also have issues, and you also have limitations that are dictated by your method, right? I ran an ERP experiment, and in ERP experiment, if you have more than one or two conditions, that's it. Like the data is so noisy that you're not able to have complex stimuli or complex combinations of stimuli in some sort. And so, you have to find a balance. And sometimes this means coming back down and coming back at the beginning and sort of reformulating your research questions, I think. So here are a few of the experiment, I think, compromises or balances that you need to find. So for example, whether you want to run it in a lab, and then we talked about the number of items and number of participants and the type of sample, for example. So about the location, I think that now more than ever is when we, now more than ever we have ability of choosing different options for running an experiment. I think until before COVID, so not talking like 5 or 10 years ago, where we had already great technology, but I think COVID really kickstarted this sort of online experiment because of course, well, you couldn't do otherwise, right? But it also kind of made it it sort of increased the speed of progress when it comes to online platforms, the type of studies that you can do online, the availability of participants online. And so before it was kind of like, all right, I want to do in the lab, and if it really comes to it, I'll do it online because I'm more limited. But nowadays, I think that unless you are working with, of course, you can't do ERP online yet, or fMRI online. So I'm clearly talking about behavioral, production perception experiments here. This is your time to go online, and don't underestimate the power of social media for collecting data. It's unless you are, again, working with clinical populations, and then it's always going to be tough to get data. And if you're working with trilingual children that speak Icelandic and Farsi, that is always going to be difficult to find your data. But if you're working with sort of like your average I just need a native speaker of English kind of population, then going online probably has now more advantages than disadvantages. Disadvantages, you can't control the environment. True. But the advantage is you can maybe get 500 people to do your experiment in a week, And so is it really worth controlling the environment if I can get 20 in the lab and 500 out of the lab? I mean, at some point, the environment is going to sort of cancel out when you have many, many more participants in a way. And so if you're not controlling for it, it's good that they're all kind of different. At least they sort of, in a way, cancel out. This, again, of course, really depends on your type of experiment. But we are going to see some example of our code later. And we're going to use this face mask data set that I've used countless times in examples and stats. And that data set was collected over the pandemic. We ran 2 experiments. And so the original experiment and a follow-up, each were only published on Twitter. And we have something like 200 participants for the first and 200 participants for the second. And it took roughly less than a week for each to get 200 participants unpaid. So the only payment was a lottery draw of an Amazon voucher or something. So, and I didn't even have to, put a leaflet up or leave the house. And again, I understand that this really depends on your population. So my population was people that can do an experiment online. They didn't even have to be native speakers. So clearly it's much quicker, it's much easier, but it's worth giving it a try. And also, before we were kind of limited to this sort of, questionnaires, you had those Qualtrics thingies where people just had questionnaires. But now, on platforms like Gorilla, we can, very reliably collect things like reaction times. We have platforms that can do eye tracking, so we are really not just limited to very, very few things. We can do many, many more complex designs. And so we kind of move on now, right? And so we talked about this already, actually. So the sort of balance that you want to do, you want to have between your design, your participants number and your item number, for example, will really come down to the type of experiment you're running, the type of participants you have, the type of effect you have. If you're looking for an effect that is going to most likely be there in the same way for everybody, but you maybe want to quantify how much, or or look at within subject nuances, then perhaps it's better to have fewer participants within a limit. Of course, it's always good to have a decent amount of participants, and more stimuli. Maybe if you are, if you know that there is a lot of like between subject variation, then you might want to have more participants to kind of account for it. Again, going back, if you run an online experiment, maybe it's better to have more participants to be on the safe side. So, I mean, rule of thumb, just get more participants. Like, regardless of what you're doing, you just can't go wrong. I had a few instances in which I was asked, like, how many participants should I get? And the answer really is just as many as you can. And there is no substitute for little data. That's it. There is no... So data analysis is not magic. It doesn't get you things that you don't have, right? If you don't have the data, you don't have the data. That's it. The only thing you can do, like I said before, is you reevaluate your research question, you scale down your hypothesis. There is no way to get magic non-existing data. And so it is always better. I can't think of an example, please interrupt me if you do have an example of cases when more data is actually worse, because I can't necessarily think of one right now. So get as much as you can, and really, and then also kind of push your boundary, well, not your boundaries, but push your, like, the limitations that you set yourself for the number of items per participant a little bit, especially if you have people in your lab, right? So, we have 20 items, it's already 10 minutes, add 10. Like, this person is already sitting in your lab, 15 minutes is not going to make a difference over 10 minutes, and you're going to get a little bit more data. Don't make it an hour, of course, but I think, like, take what you expect your experiment duration to be, and don't be afraid to add like a 10% just to say, it's always good to get a little bit extra data if you can squeeze it in your, it's easier to do it online, in the lab, because if you do it online, you have the risk that people stop doing it, right? So if you start adding more and more stimuli online, then people just get bored halfway through, and then you basically are left with a half-finished experiment, which I would never use, because you never know why it's half-finished. Is it because the person got bored? Were they even paying attention in the first half? And so at that point, maybe it's better to have, don't push the limit of amount of stimuli, and also, keep it, keep in mind what kind of payment or, thing that they're getting. Sometimes I do get, links online, and, we're looking for Italian people to do an experiment, and I click on them, and, I'm like, oh yeah, I'm happy to help science and do an experiment. And it's like, this experiment will take you 45 minutes. And I'm like, I'm sorry, it's really difficult to expect somebody, out of their own free will to do 45 minutes of a free experiment online. And also, online is also prone to many issues. Over 45 minutes, you could have a disconnect. You could have, issues with the internet and so forth. And so eventually, even if this person was willing to sit there for 45 minutes and do an experiment, then, they might have issues where it doesn't, I think some platforms are helping with this, so that they allow for like reconnects, they check your IP address and things like that. But it's always, good to keep in mind what people are going to do. And of course, this applies even more, but of course, people that do these kind of experiments know it way better than I do. If you work with children, for example, I suppose you can't expect a child to work to do a 45 minutes experiment where they are concentrated doing something. Again, but we're kind of entering the realm of specialized advice here, and I don't know much about running experiment on non-adult population. So it's better if you sort of. Yeah, and one thing, we haven't mentioned yet is remember the type of sample you collect is important. And again, if you're working with specific population, this might not apply to you as much. If you need trilingual people of that type, you already know what kind of population you have. But especially if you're running, if you're running sort of like general population experiments, or just need to be an English speaker kind of thing, maybe don't hire only bachelor students from the psychology department, right? So I think this is one big issue. But it's a big conversation being had now in over psychology. For example, where 99% of psychological experiments are done on bachelor psychology students, but then they try to generalize this to the entire population. So you have a lot of these psychology experiments done in very affluent universities on rich or more affluent or okay, let's take money away, but more educated younger people of a certain specific generation and a specific type of education are not representative of your entire population by any stretch of the imagination. And sometimes it might not matter. Again, I never cared about it when I did my experiments, because I was looking at sort of just perception, like literal perception of sounds, and there is an argument that is too sort of bottom up kind of thing, that it shouldn't matter as much whether you are a psychology student or not. But it's good to keep in mind that getting a varied sample is important to getting balanced data. And so here we have, to conclude this production section, a few tips again from maybe my experiences. Like, write everything down, like what hardware you use, what software you use, everything. Just take notes as you go, because especially if you're doing like a PhD thesis, I think like if you're doing maybe in a paper you don't have to go in as much detail, but in my PhD thesis I went down to like what type of speakers we use and what type of monitor we use, and for every software that I used, what type of version of that software was used, on what on what operating system was it running, so on and so forth. So and this might and this is good for reproducibility as well. I mean, it's definitely good to report in your PhD thesis. I think you might not go down to the tiniest detail in your paper, but you still report the majority of the details. But also it's good for reproducibility, which is nowadays more needed than ever. Make sure you have all the forms that you need, participant information. Make sure your participants know who to contact if they run into issues, if they want to withdraw from the experiment, if they don't want the data. Anonymize data whenever you can. Make sure that you have practices in place for data protection and storage. What are you going to do with this data once you collect it? And so we talk about this already. And then if you can, hire a research assistant. They're life-saving, and there are so many mistakes to be made in during a data collection that having somebody to help you there, it's crucial. And I guess it's not here, but especially if you're part of a lab, make sure you have some protocols. Make sure you have protocols for doing things. That way you can have multiple research assistants. You can have one after the other. You can keep that protocol running for years, and even if you change research assistant, you can keep some continuity. And you make sure that if you keep more things as constant as possible, you can be also more sure about the quality of the results that you're getting. Any questions so far before we move into the last section here? So this is the post-production per se.
I don't know if this is something we can discuss now, or I don't know, but I'm just wondering, when you said the more data the better, that I was taught, I think, to have also stopping rules, to decide before you do the experiment when to stop data collection. Because I think, if I remember correctly, Bodo Winter has in his book, right, also this graph where you kind of claim significance, and if you had collected more, then And I was wondering about this, and to what degree you would recommend to implement this stopping rule, and how, because I was always puzzled by this and I never understood really how to do it.
Well, I think it makes sense, but and you're right. So I think I wouldn't just kind of just like start data collection and then just kind of like let it go until it ever fills up, or until I have n participants. But maybe the way I mean it is like get as much data as possible, that you know you're going to need, right? So it's also not necessary to get, or it's also, you know, detrimental to get, you know, too many participants, as you say, can inflate some effects and things. But the idea is, if you know you need 200 participants for a certain experiment, for a certain effect, then, you know, aim for 200. So I think that it definitely makes sense to get, so I think it's good to like look at the literature, see what is considered a sort of safe amount of participants for the effect or the study that you want to run, and sort of like aim to get as much of the data that you can for that, right? So I think, yeah, I think you're right. The way I phrased it, it kind of sounded like just get infinite data. But to be honest, in most of what we do, it's so difficult to just get too much data anyway. I think we really run the risk of getting too much data that it inflates our effects. But you know, I think like, you know, have an ideal number that you come up in advance and try to get that number without compromising. That would be maybe the best way to phrase it. Yes. Any other questions? Okay, so editing. So know your data. Know your data is probably the best advice. Again, on the part, you have collected your data. Now you're down at the post-production stage. You're going to pre-process your data. You're going to you do some data wrangling, and you're going to analyze it. And the way you do this is really going to come down to the type of data that you have. So this is important. You know your data best. What type of filtering, if you need to do some filtering, or you need to do some whatever you need to do to it, really depends. And something done wrong here can you know, cause you to have issues later on. But actually, let me tell you one good thing about this part onwards, is that usually any mistakes you do after data collection, before you submit your paper, can be fixed. So I think the good thing about this section is you know, if you have an experimental design that's too complicated and you acquire data for it, then that's it. You have collected your data. The only option you have is you go back and do it again. But now that you have your data, if you know how to deal with data, everything you do now can be reversed. So you know, don't worry about it too much. I think this is the part where you can take the more sort of, in quotation marks, sort of creative approach, right? Here, if you make mistakes here, it's okay. You can plan ahead, but also, like I was saying before, you can plan multiple routes to take and compare these routes and see, okay, which kind of model should I use, and which kind of filtering I should use. So when I did my PhD and I was working on ERP data, there is a clear but also not very clear pipeline of things you should do to EG data before you can analyze it. And if you look at different papers, you know, you have so many different possible combinations of all these things that you can do. And again, you can take your time and kind of like figure out which one do you think works best for your experiment, which one is, you know, the best pipeline or whatever. And but you can always kind of go back at this point, or you have your data. It's always good to keep your raw data available. And, you know, if you're working R, sort of take this constructive approach where like you can just create new variable, new data sets with modifications, but that way you can always kind of go back to the first step. And so, okay, so now we have a look at some R code, which I'm not sure why it made it into that slide. But I need to unshare my screen, and I will share my R. Where is it? Here. Okay, so again, it's not important here that we know. You know, it doesn't matter if you don't code in R. It's okay. It just to kind of talking about an example here about data processing. So we're going to use this face mask data set that I've always been using as an example, and I mentioned it a couple of times as well earlier. So we have information about reaction times here in milliseconds for basically participants are presented with a word, they're spoken to them. This word contains a fricative. They have to guess which fricative is present in that word in English. You can see the words here in the item column, and then you have the fricative column. And then you have two conditions, basically, no mask or with mask. So the speaker is either wearing a face mask or is not wearing a face mask. Okay, right, so this is the data set. And so we want to see, for example, are there different reaction times based on, of course, whether the speaker is wearing a mask or not wearing a mask, but also based on the type of fricative, because, for example, fricatives like TH and F have visual cues, so you can see the lips moving, and so you would expect that without a mask, it's easier to identify whether something is TH versus F, but with a mask, if people do rely on visual cues more or as much as they do rely on acoustics, then it can become a little bit more problematic. Okay, and so again, this is just kind of a setup, and we're working here with reaction times just to have an example of how different pipelines can change things. And until like I would say like maybe 10-15 years ago, before LMER became like really popular, so mixed models, what would happen is that you would calculate sort of the aggregated measure. And so take, for example, participant 1, what is the average reaction time for this fricative when there is no mask, and take, you know, the mean, and then participant 1, same fricative with the mask, take the mean, and then you would put you would use an ANOVA. Now that we have access to, for example, linear mixed effect models, we can use the sort of raw observations of this data. And so you can see that, for example, we have about 11,000 what do you say, observations here. So we have quite a few observations per participants. We have about 170 participants in here, I believe. And so what happens here is that with reaction times, again, we used to aggregate them, and aggregated data usually is distributed normally. So then we can use an ANOVA to test it. What people have been doing recently, or a little bit less recently with this kind of data, is that we transform the reaction time. So we transform them using a logarithm. In this case, we use the natural logarithm. And what log transforming does, it kind of takes the edges of the distribution and it kind of squishes them towards the center, which is in a way good to control for outliers. And you do get quite a lot of outliers in reaction times, because it can take, you know, if you don't put an upper cap, people can take infinite amount of time to respond, right? And so you might have an average of, you know, 600, 700 milliseconds, but then somebody can take, you know, 2 seconds, 5 seconds, 10 seconds, 20 seconds. So you get a lot of those outliers that get squished with when using, you know, log transform. And so one way to do this would be to take our log reaction times here, and then we have the condition, and, you know, we have our model, we have a linear model, mixed model, we run it, and our dependent variable in this case is the reaction times after they have been log transformed. Okay. Another way to do it would be to use the reaction times as they are, so not log transform them, but we specify the actual distribution. So the reason why we log transform data is because it's distributed more normally. But now we have also access to models that let us model non-normally distributed data just by specifying, actually, you know, this data is not normal, it's distributed as a gamma distribution. And there's kind of a shape that I'm telling you about. It looks like kind of like a normal distribution, but has a huge tail on one side, and that's all of your outliers. And so, and also we use this link function. It's a bit of a complicated concept that kind of maps a nonlinear to linear transformation, and we say log. So ideally what we're doing is we're not log transforming our data, but we are creating some estimates in our model, and then we're log transforming it. Sounds similar enough. And so we run this. It takes a little while longer, but it does work fairly quickly. For some reason, I have this too. Oh, and the reason is, okay, so these two methods should be fairly similar. They should give you pretty much the same results. But what happens is that one doesn't quite work unless you remove your outliers. And so I also removed some outliers in the other one. And now we'll show you exactly what's going to happen. But so we have these two models. They should be fairly comparable one to another, the same data set. But then if we run our model and then we look at our plot coming out of these models, we can see that, so these are the estimates for reaction times So reaction times on the left, so on the y-axis, and you have red and blue. Red is no mask, blue is without mask. And so, for example, if we look at the very first one, you have F, and you can see that they're roughly the same, red and blue. So it means that no mask, without mask, there is very little difference between the two of them. And it's very similar for all of them, but not the same, okay? And in this case, there is not a huge difference among them. They're probably all not going to be significant in the same way, and it's okay. But you can see that, for example, S, so the third one, behaves differently than S from the second model. So the first model is when we log transformed our data. The second model is when we didn't log transform our data, but we used a log function on our model. So we can see there is a little bit different from S. There is also a little bit of difference from F, although the end result is going to be very similar. But also there is a third way to do this kind of modeling, and that's to just use the default gamma option. That's what most people would use, I suppose. And if we run this, what happened here? Yes. So if we run this, just saying gamma without specifying this link function, it works now. Let's see if that's also a little bit different. It looks also now a little bit different again, not too much. But also, for example, it only works if we remove some outliers. So this code line here removes some outliers. But if we don't remove the outliers, if we keep the outliers in, this model doesn't run anymore. And so, again, the point here is not exactly to learn the code, it's to show you how I took one data set and I used 3 different ways to do the analysis of this data set. And they are all okay, according to the literature. So there are literatures that shows how to use this, all 3 different ways to do an analysis. And not only did we get, okay, similar but slightly different results, but also in one of the cases, we were not able to, this model was not converging unless we removed some outliers. While, for example, if we take the original ones, the RT log one, where we log transform the data and we don't remove the outliers, so you can see this line is kind of commented out, then it works, right? So technically it's the same data, it's very similar models, but you do get issues. And what happens is that if you do this and then you get an error, then you might think like, okay, maybe I need to simplify this model. And then you're, eventually, whatever happens, and you end up with different results. So again, the point here is not the code. The point here is there are many different ways you can do something, even when it comes to data analysis, and even things that appear to be very similar to one another can actually be fairly problematic. So just pay attention. Okay, I will now share again my slides. So we're done with the code. Okay, right, there we go. Welcome back. And so here is a few references for your for what we just seen now. And actually, we also didn't mention the outliers quite as much, but that's also something that I would kind of want to keep referring to, is that a lot of the times people come to me and the idea of removing outliers is almost already kind of ingrained, and I would want to sort of dissuade you from that, because I think that removing outliers should be something that you do if you necessarily have to. But even then, I would do it very, sparingly and very conservatively. And there is a reason for that. I mean, nowadays we have the ability to have this, very complex models with a lot of observations in. And if your outliers are, as the name suggests, just outliers, so they are a very, very small percentage of your data, then it really should not be too much of an issue. Your model should be doing the same things. And I've, tried it, anecdotally. So of course I don't have a reference at hand, but a lot of the times if if your model works and you remove a very few percentage of outliers, if there is a real effect, you should be able to see it regardless of whether you remove outliers. The second point is, if you're going to remove outliers, do it conservatively. here is a good reference. On the screen, you can use, wait, am I sharing the screen? So a good reference to use the, what's it called? The median absolute deviation instead of the standard deviation. So the standard deviation around the mean is usually, you know, one will say, okay, I will take like the mean, 2 or 3 standard deviations, and I remove everything that's outside of those things. But actually, the problem is that your standard deviation and your mean are affected by the outliers themselves, right? Because, you know, if you know, a good example, if you have a class with 4 students and they are, you know, 5, 6, 7-year-old, and then one is 100-year-old, your mean average, you know, your average age is going to be quite higher because the 100-year-old is going to skew that number high up. However, if you do take the median, it doesn't matter if, you know, one person is 100, 1,000 years old, 1,000,000 years old. If the rest of your population is, you know, 5, 6, 7, then the median is going to be 6.5, you know, between 6 and 7. And so using the median, and then instead of the standard deviation, you use the median absolute deviation, which is kind of a similar thing but calculated on the median. This allows you to get a more sort of correct estimate of what you should be looking at removing. So this is a good suggestions, I think. But really, don't go there unless it's necessary. And you know, outliers also tell you a lot. I mean, if you do have 15% of outliers in your data, I mean, what is that really telling you? I think that's you know, I think there's an underlying problem there, because really, you know, is 15% an outlier still? You know, that's quite a substantial percentage. And so that maybe is telling you that your design wasn't as, you know, it wasn't eliciting exactly what you were expecting to elicit in such a big portion of the population. And so you know, treat outliers carefully, because they sometimes tell you a lot more than you think they're telling you. And if really they're such a small percentage, then you shouldn't even worry about them in the first place, and they will be there. Any questions so far? We're closing in. We should definitely finish on time. And okay, so modeling. This is another thing that I think a lot of people get wrong sometimes, is that, you know, students might come to me and say, like, this is my data, and now what do I put in the model? And I think that this is kind of, again, like the wrong approach. And you know, you need to kind of go back to this idea that you should plan everything in advance, and your most complex model needs to be in a way already predetermined before, because that's going to be determined by the experiment you run. Okay, so if I'm going to test whether people have different reaction times when they see, for example, they hear certain words with certain fricatives in them in both a non-mask and mask conditions, I already know that I have different fricatives. I already know that I have different mask conditions, and I expect there be an interaction between these two. So I expect fricatives that have certain visual cues to be affected more by the mask than other types of fricatives. And so I already know what my main predictors of my model are going to be. So before I even run the experiment, I know I'm going to have a fricative predictor, I know I'm going to have a condition predictor, and I know they're going to interact. I know that they're going to have different items. I know that each item is going to have different lexical frequency. I know that lexical frequency plays a role on reaction times, and so I know I will want lexical frequency in my model. So ideally, at least for when it comes to the main experimental predictors, you will already know what you want in your model before you even run your experiment. And then, of course, what mixed models allow us to do is to kind of add things that are not necessarily predictors of our experiment, but things that we want to see whether they're kind of correlated. So things like, you know, questionnaire answers, you know, like, oh, does this person's age, for example, affect? And those things are things that you can sort of try later on. But really, you know, your kind of main structure should be fixed. Another issue I find often is what is a fixed effect and what is a random effect in your model. This can be quite tricky. There are a lot of different opinions on what constitutes a fixed effect or random effect. There is not real consensus. What I like to think as a fixed and random effect is, so I think that there are, in a way, certainly limitations first. So if you have categorical variable with many levels, it will just doesn't work as a fixed effect. It's just too much to include it as a fixed effect in your model. And so things like participants, for example, you have 70 participants, you will want to include them as a random effect. And we often talk about a random intercept or varying intercepts. We'll talk about slopes in a little bit. But also at some point it comes down to what you're interested in as well. So, a random effect, a varying intercept, I kind of see it as something that, you want it to be there because it's important to the dependency structure of your model. So what a random intercept basically tells the model, it's kind of saying, look, there are 100 participants. The data coming from each participant is going to be more similar to itself than to the data coming from another participant. So what this is meaning is I might be slower or faster than you at doing that fricative experiment, not because of the masks, not because of the fricatives, or because of lexical frequency or anything, just because of me as a human, I might be slower or faster than you. But it doesn't matter because we're looking at within subject. So we're looking at, it doesn't matter if I'm generally slower than you are, as long as within myself, I am, for example, slower when there is a mask than when there is no mask. And this is what your random intercept for participant is kind of telling you. But at the same time, you're not going to get information about significant differences because you don't really care as well about whether participant 1 is significantly different than participant 4 and participant 3 is significantly different from participant 7. And also it would be just too many comparisons to run. And so it really, I think, comes down to it, the level of resolution you're interested in. So is this something that you are interested in seeing whether there is a significant difference? Are you interested in estimating the exact levels for each of those, the exact estimates for each of those levels? Or are you just wanting to make the model, aware, in quotation marks, of the presence of this dependency structure, whether that be the participant, the items, certain words might, certain sentences might, make participants react differently, regardless of the experimental condition, just because a certain sentence might evoke a certain response, a certain emotion, for example. And slopes galore. Include slopes in your random structure. Again, it's difficult to find a balance for this kind of workshops. The idea is, I need to assume that you all have some understanding of these things, because otherwise it would be a 6-hour workshop. But hopefully, so if you are familiar with linear mixed effect models, like we were saying, this random intercept is basically kind of telling the model that there are some baseline differences between the levels of that predictor. So when you say random intercept for participant, you're kind of saying some participant might be slower or faster than other at reaction times in general, regardless of the task. And what slopes do is basically saying that a certain predictor, so you include a predictor of your fixed effect, you include it before your participant in a specific way in R. And what is this saying? It's basically saying different participants, not only do they have different baseline differences among themselves, but also they are affected differently by a specific predictor. So let me give you an example. We have this reaction times and we have this condition, mask, no mask. What the participant intercept is basically saying is, regardless of whether the speaker is wearing a mask, participants might be faster or slower just because they are different human beings. But if we put a slope of condition over participant, what we're saying is, we're saying not only are different participants faster or slower because they're different human beings, but they're also affected by this condition differently. So for example, I am short-sighted, so I don't rely on visual cues as much. And so I don't think that a condition like mask on is going to affect my reaction times as much as it's going to affect somebody who relies on visual cues much more, for example, because maybe they're hard of hearing, right? And so different aspects. And this is really important. And why is this important? And I know people don't like slopes for this very particular reason. They a lot of the time they kill your significant results, because if you don't include a slope, your model might attribute some difference in the data to the main effect and might say, well, there is a main effect of this or there is a main effect of that. But once you actually include that in the slope and you say, well, actually this difference might not be caused by the actual predictor, but it might be caused by this individual differences, then a lot of the times the significance of the effect disappears, and it's never the other way around. So usually whenever you include a slope, it's never going to be good news after that. Okay, right. So I mean, sometimes it's straightforward to process your data, like reaction time. In a way, it's not as complicated because you have your reaction data you either log transforming or not, and then you put it in the model, and then you have results come out of it. Sometimes it becomes quite complex, such is the case of ERP. And of course, the more steps, the more arbitrary decisions you have, the more you tend to you increase your chances to fail. And that's kind of why I don't like removing outliers. The idea is that you are introducing an arbitrary decision. How many outliers is it okay to remove? Is 3% okay? Is 5% okay? 10%, 15%? And at some point you basically you're very open to, well, first of all, malicious practices. One could just kind of start removing outliers until you get a significant result. But even in a non-malicious way, it just adds a layer of arbitrary decisions that you have to justify, and you open yourself up to a reviewer saying, why did you remove 5% of the data? Why not fewer points? Why did you find it necessary? How can you justify it? And so the more arbitrary decisions you add in your data analyzing process, I think the more you are vulnerable to this kind of points. Of course, sometimes it's necessary, and of course, sometimes it's justified. So if you do have the means to justify your decision, I think it definitely can be a good option. Okay, reporting your result. Sorry, yes.
A small question. So do you think that 1% would be okay if you remove 1%, just to have approximately?
Yeah,
you said 5% that may already raise a flag, right?
I think some methodological paper recommend like 5% is the upper possible threshold to have. So I think ideally within 5% is what's considered sort of in the acceptable range. Yes, so 1% shouldn't be an issue at all. Yeah. Okay, so now you have your results. You have your models, whatever you've done, and now it's time to report it. And I think that it's good to have some reporting practices. And first is standardization. So try to standardize reporting your results. A good way to do it, a really easy way to do it, is you have to report the results of a test, whatever test that is, chi-square test, t-test, because they're part of your model. Just type t-test APA, chi-square test APA online, and you get like the precise exact way to do it. And sort of like, to report a chi-square, you need to do like square bracket, the chi-square symbol, and then you open bracket, you include the degrees of freedom, and then equal. So you have like the precise standardized way to do it. Standardization, I think it's always key. And I believe the results section should be the most should be the least creative section of your paper. Like it should just be, a bunch of like really clear table and data visualization. Provide supporting material. I think that we're all moving in this direction nowadays, but if you can provide, files like the R Markdown files that I'm providing you as sort of a companion to this workshop, do it, because it's good. And it's also good to clarify things, right? So if I decide to run an analysis, but I know that perhaps there is a second possibility, but I don't want to like take a paragraph of my paper to do this. I can just include the R Markdown file or the knit version of it, where I can also show like, okay, I also ran this other analysis, but eventually I decided to go for this one because, and so you might, stop a reviewer from asking, questions to begin with, or, in general, it's more open. I find it very, I find it's the direction we should go towards is, let's science is hard. Like, let's just make it a little bit easier for everybody, and kind of, we don't need to gatekeep the code that we use for models. And I think, if we help standardize things, it's just for the better. To help with these things, you can use package report in R. This was a discovery from last year, and I have never stopped using it once. And what you're seeing right now on the screen, I have not written a word of. It's your package report. You run it on a statistical model, and it comes out with text that kind of tells you in a standardized way what will happen. And of course, I haven't touched it here, but you can then go into the text and change the name of the predictors to something more meaningful for your paper. You don't have to include the last 2 bullet points, for example, but it gives a nice way to start structuring your results section or describing what you've done in a more standardized way. And one of my favorite features is this report for the session info of the R, and so it tells you like exactly what version of R you're running, on what computer, what packages. And also it provides you, it's not in the slide, but it provides you with a complete reference list of all the packages you've used. So even for that, it's already worth it. You don't have to look for it. You just have all the reference list there, and then you can copy it. And it helps the process being a little bit more open. You don't have to copy in the paper if you want to, but I always add this at the bottom or at the top of any R Markdown file. So when I send this R Markdown file to somebody, they know, for example, what version, what package I used, and also for yourself, because it's, I'm teaching stats in R, and it's my 3rd semester now, and there's already a few slides, a few lines of code that they don't work. And, because packages update and things change, and so even things that I've written a year ago are not working the way I intended them to work now. And so it's good to keep in mind what version of package you use to run an analysis, because 1 year from now, if you rerun it on an updated R version, an updated package, you might not get the same result. And that's not great. So now you have you shot your film, you have your edited film, and now it's time for the nicer part, is the color grading. And in your data experiment journey, that would be your data visualization. And here I've added a little fun picture from the same series from where we started, and it's a great picture to tell you basically the main advice I have in terms of like colors and data. Don't mix red and green. Those are the 2 worst color you can put together. And I think like here in this scene they work very well. It's a very dissonant combination, and it makes you a bit uncomfortable. But the reason why you would not want to do it in a data visualization environment is because red and green are 2 colors that colorblind people cannot differentiate very well. I don't remember. There are different types of colorblindness. For the life of me, I can't remember the names of, but I think the most common ones is the one where red and green hues are kind of like mixed together. So if avoidable, always avoid to use red and green. And there are simple solutions to have good colors and good data visualization. And so let's talk about this for a second before we actually jump in some examples of ggplot. There are some packages. There is a package called Viridis in R. I'm not sure if it's available with Python as well. But what this package provides is a set of color scales that are perfectly weighted to work in many specific ways. So they don't affect anybody with any type of color blindness in any way. They are perceptually sort of like balanced, meaning that a lot of the times, especially when you see things like rainbow colors, the distance between certain colors perceptually for us is not the same across the entire range. So for example, blue and green might appear closer to R, than red and yellow. And so when you look at a visualized data, this difference might seem bigger than what they actually are. But also it's really important that your visualization works in black and white. So Viridis provides you with colors that even if you print your paper in black and white, you're still going to see based on the luminance, and so based on the brightness rather than on the color itself. And so you have one package, you have everything available to you in that one package to create some perfectly balanced and nicely done graphs. When it comes to data visualization, I prefer to plot model estimates like we saw before in the example in R when I showed you those different examples for the two models. They are not, beautiful plots in a way, but they provide good information about what the model thinks the estimate is and the confidence interval. I find that more intuitive and I find it more useful than just plotting raw data, as raw data can be affected by so many different variables, and you have outliers in there, and a lot of the times you end up making things such as a bar plot, and that's just like one data point most of the time because it's like the aggregated average of everything. It doesn't really tell you what the distribution is, because again, if you just provide the mean of something, this doesn't really give you too much information about the standard deviation. Yes, you can include error bars of some sort, but I don't find it particularly useful. You also can create this estimate plots in different ways. So you can use the package sjplot, is the one we saw before, and that's a very straightforward way of doing this. So you basically tell it what the model is, what things you want to see, and it creates it for you. Or you can use the package ggeffect and ggplot combined, and that's kind of do-it-yourself kind of way. So the ggeffect package provides you with the same number that sjplot uses to make the plot, but it just provides you with the numbers. And then you can take the numbers and do whatever you want with them. You can plot them however you want. It gives you a little bit more freedom. I actually have some R examples of this, but we're running a little bit late. I think it's, it's not really necessary at this point. And again, less is more. Really, I think that this comes down in general to data visualization. I find that have fewer plots, but have, more, like focus on the, on the research question. Even if you have 15 effects, like I know that lexical frequency affects reaction times. I don't really care to see that. I care that the model knows about it so that it accurately predicts my estimates, but I don't really need a plot to show me how lexical frequency, does increase or decrease the reaction times. That's a given. And so I wouldn't include a plot on that. In the example that we looked at before, I would include a plot only on the condition and fricative. There are ways to combine these plots together, make them a little bit more tidy. And so I find like less is more in terms of both fewer plots are better as long as they are more focused on what you want to show, as well as make plots, fairly simple. Don't start to mix, 70 lines and dots and things, and it becomes very, very, very unreadable. Here is the package Viridis I was telling you about. Also differentiate with shape, not just with color. So, if you have multiple lines across a plot, maybe consider have a solid line, a dashed line, a dotted line. This helps a lot for, if somebody's printing this in black and white. Any issue with color, it's great, and also it just, even if the color is visible, it just adds an extra layer to make it easier, to make it jump right to your eye to see exactly what the difference is. And also, needless to say, label everything clearly, right? So nobody wants to see a plot without axis labeled. And also, finally, don't cheat. I think this is not as common, I think, in the scientific community as it is in the maybe sort of media community. But you always see those like bar charts when it's like, there's a crazy difference between these two bars. And the number of people that do or don't do these things, and then you realize that when you look at the y-axis, the both bars start from like 80% and they get to like 83%, and then one of the bars is like 81% and the other is 82%, and like the difference looks so big because the scale has been reduced to a point that it makes that difference look massive. But if you take the entire picture in, then you will see that the two bars are fairly comparable. And check with journals. I think it's important. Sometimes some types of journal might not allow figures with colors, or they want a specific format or whatnot. So it's good to be able to be flexible. But if you kind of follow these rules and you try to make sure everything is labeled clearly, and you differentiate with things like shape and dashed line, or when you have dots, you can put like different shaped dots and stuff like this. Then you are also kind of making sure that you are able to comply to many different types of journal requirements. Okay, finally your movie's done. You can now go and present it at Cannes Festival and hopefully get a prize. And the same you can do with your paper. It's time to get it into the world, and then you will have conferences and journals, and if whenever possible consider open access. I think that is my only kind of advice. And again, I want to repeat this, if possible, consider sharing your data and your code with your paper. I think this is the best way to advance both science, but also methodological, and we shouldn't let our, egos in a way, kind of take the best of us. I've seen, many comments of people saying like, but it took me, years to come up with this code. Why would I just give it away? Because it's, but I don't think thinking this way helps the field. And nowadays, I think more and more journals are actually mandating the inclusion of your data sets with your experiments. And so the more sort of good habits you follow in preparing your data set, the better your presentation is also going to be. The easier it's going to be once you get at that stage of submitting a journal article. If you've done everything in a tidy way, your code is tidy and well commented, and your data is tidy and saved in the correct format, it's less work when you get at that point to get it out in the wild. So this is the end of the workshop. Here's a few references more. And I'm happy to, we made it to almost exactly 2 hours, right? So I'm happy to take some questions now, sort of like general questions about any of the things that I mentioned now. So we are still not at the point. So try to avoid questions like I in my experiment, unless it's sort of like still like a general question, I would say.
Hi, Max. So I would like to ask a question. Let me turn on my camera. So first of all, thank you for the workshop. I think that's really inspiring, and I think everybody learned something here. So we were talking about removing outliers earlier, and we had the example of reaction time data. And I was wondering if there's sort of different thresholds, maybe you could say, for different kinds of data, right? Because for reaction time data, I think it's actually fairly reasonable to assume that some points are outliers. If you have, like you say, most of the data points like around 600 milliseconds or so, but then you just have, because you conducted an online experiment, data points that have 2 seconds, 3 seconds reaction times. So could you be more lenient in cases like that than in other cases where you want to remove outliers?
I suppose so, yeah. I think like another thing about reaction time data, for example, is that usually you analyze reaction time data of correct answers when you're doing this kind of experiments. And so in a way that a lot of the time that takes away a lot of outliers as well. If somebody's going to take 10 seconds to reply, they're also less likely to maybe reply correctly. But definitely I would definitely say that it takes the different thresholds are applied depending on the method. But also I think within each method you would want to be, I think you can have like more conservative and less conservative thresholds as well. And I would always lean for the sort of more conservative approach. So, in ERP as well, you tend to remove outliers. You don't do it in terms of like reaction times, of course, but you go maybe and take like, if you have like peaks that are too high, there could be like blinks and stuff. And so what you do is you need to set a threshold and say like whatever is above this, take it away. And there's an argument for being more cautious than not. But like I said at the beginning, it's always difficult for me in a situation like this to speak to a specific example because all the fields are so different, right? And so I'm kind of just providing a sort of general kind of rule to live by, and then it's up to you to just like check what what your method is, but also what your population is. I understand that you're learning, like populations like clinical populations and children, data tend to be a lot more noisy, for example, and so you need to have different thresholds. But maybe if you know it advanced, then maybe you can get more data, right? So if you know that you're going to throw away more trials per participant, so it's not a problem maybe of a single participant, but a few trials per participants, you might want to get more in advance. So I think it's all about like striking this balance of knowing beforehand so that you can compensate before you have to compromise.
Okay, thank you.
You're welcome.
Hi, Max. Thank you for a very interesting and rich workshop. I had a question about including the slopes in your model. So I'm also a big fan of including those. However, most of the times I do run into convergence issues. So how do you deal with that? What would you recommend?
Well, I think that the only way at that point is to simplify the model, right? So I think like my take is, so when you start, so when you work with your model, make sure you include them to be sure that they are there. And then if they don't work out, then you can remove them, right? So I think that there is sometimes it just doesn't make sense for there to be a slope in terms of like, it does, but hey, perhaps there is no effect of this condition, for example, on participant, and that's why it's not converging, right? So this effect is so small that it cannot be estimated, which in terms simply means there is not a lot of variation, right? So it's not necessarily a bad thing. And so what that means is that, well, if there is no variation, then you might as well just remove that slope, but at least you tried it, right? So that's the key factor, I think, is that you definitely want to make sure that it's there. And then if it turns out that it doesn't work out and you can simplify, remove the slope. Sometimes even just an intercept needs to be removed if you have too many, for example, random intercepts, right? And I think like this is also where it helps with, if you submit your code, for example, with your paper, I always tend to do this like, like I run a model and I show that it's a singular fit, and then I rerun the same model below without the slope, so the reviewer can just look at it and not ask like, where's slope, for example.
Okay, thank you.
Can I ask an add-on question to that? Because so assuming that you have a very complex random effect structure, and then your model doesn't converge because you have a very complex random effect structure. So is there a rule of thumb on what you should remove? So usually I think you would remove slopes first, right? And then intercepts if you have to.
Yeah, I think that's how I would do it, yes. But it's also like important to say that if you have enough data and your effects are really there in terms of like, there really is a difference. So there really is a random effect things happening, then you will not have issues. So I think like with the data I was showing you before, where we had like 12,000 observations, over 170 participants, I think we managed to have something like 3 different random intercept, and then for each one of those 2 slopes, and it would still converge. Because eventually, if you do have the effects, if the effect is there and you have enough data to provide, to provide a model for estimating that, then you will not have issues in that respect. The only 2 times I would suppose where you have issues is you really have those random effects there, but you don't have enough data, and so the model doesn't converge, or you have enough data, but the effect you're trying to estimate is really not there, and so your model is basically telling you there is nothing to estimate. So it's, I think like what you're saying is correct. You would remove the slope first and go that way. but like ideally you wouldn't do that either.
Of course,
I think.
Of course. Yeah, and then if you, as you said, if you had multiple slopes, should you prioritize one slope or the other, or would you just do like a sort of trial and error and remove one slope first and then see if it converts then? Or
I would do trial and error, because a lot of the times it's not just even about the number of slopes, it's maybe about a specific slope. For example, if you have like the slope for condition, for the example we had before, right? And then so the idea, like different conditions affect reaction times differently for different people. And then you have like lexical frequency, a slope for lexical frequency. So the idea, lexical frequency affect reaction times differently for different people. And you get a singular fit. It might not be that the singular fit is because you have two slopes, but it's because you have one specific slope. Like maybe it's the log frequency 1, because, for example, there might not be a difference among the participants based on this log frequency, and that's why you're getting that singular fit. And so, you could go ahead and remove 5 other slopes, but if this one is the problematic one, you will still get the thing. So I think it's actually good to do like this trial and error thing, because you might just be, you might just get away with removing like the one particular slope that is actually the problem. And, but if you don't know it, you just start removing other things, and then, that's an issue as well.
Okay, super. Thank you.
Okay, I will stop with the recording. Am I still recording? I hope so. Doesn't look like it though.
No, I think you're still recording. There's still a little red light blinking in the top left of the screen.
Because usually I have it's at the bottom, you have this like start, stop, pause thing, right? But there it goes. I guess my page